Hey gang, how you folks doing? Oh, the music was super quiet. I forgot to turn the volume up. Sorry about that. Hope you are doing well today. Got a couple things on tap. Not actually a lot left to do with our lists or our maps, right? Maps and hash tables. So we looked at what that looks like. Right? This idea that we create an oversized storage array. Let me pull this down here. Bring up Canvas. Oh, I have to log in. So that we can store things based on the hash and then look for whether or not an object equals. So the math behind it means we can get constant time inserts, we can get constant time lookups, right? But there's no order. So there's a little bit of a downside that it's not an ordered type of data structure. We'll look at the ordered ones next week when we look at our binary search trees. That's a great ordered data structure. But if we don't need order, then the hash table is fantastic for speed. Come on, let's load. Here we go. Yep, and we'll look up search trees. We'll get to sorting and selection a little bit, ethics, and we'll work on that final project. So we do have the current project coming up due with your linked objects, right? It's not a linked list. It's the object itself, like the term in the polynomial links to the next term. That's due in a week, right? A week from today, we've got to get that one in. So we're doing a couple operations, right, with polynomials. Remember, they work a certain way. So I'm going to pull up my whiteboard. Right? Whether or not we're adding polynomials or multiplying polynomials, differentiating or integrating here. Right? If we have a polynomial like 3x to the third, and we want to add that with another polynomial, say like 4x to the third. Right? Well, what do? If the exponents are the same, we just add the coefficients. Now we have 7x to the third. If they're different, say if we had like 3x to the third plus 2x to the fourth, well, what we get here is 2x to the fourth plus 3x to the third. Right? Remember, these don't change. Right? We create new results when we do this thing. Always new results. Okay? Math doesn't change the originals. It creates new results for us. Okay? And then say if we wanted to multiply. Right? What happens, say, if we wanted to multiply this one and this one? Sure, we could do that. We're going to make a new result. Right? Wow, my math is failing me at the moment. Where's all my math prof friends? Oh goodness. When we multiply, right, we multiply the coefficients and add the exponents, right? So we would get 14x to the 7th plus 21x to the 6th. Is that right? That sounds right. Multiply the coefficients, add the exponents. Wow, I'm going to Google it because I don't want to be wrong here. Multiply polynomials. It's got to be it, right? Multiply the constants. Oh, goodness. Mathisfun.com. I love it. I believe it. Let's make sure we're doing this right. Right? Multiply the constants. Yeah. Perfect. Okay. Yes. We got it. We got it. We're doing it against 2. Good. Okay. Got it. Got it. Now, don't forget, though, our coefficients here could be negative. Don't forget. Right? Could be negative. Watch out for that. So one of the things we need to do is turn this into a string in descending exponential order, clean up anything that's x to the 0, and don't add a negative. Right? Make sure we're subtracting when we turn things into strings. Okay, so we can multiply. If we were to multiply both here, this is where it gets fun, right? So maybe we had, let's do another example here. Let's say 7x to the third plus, I don't know, 4x to the fifth, right, is 1 times, let's go, I don't know, 3x to the fourth plus, what do we want here? Another value. I don't know. How about 2x to the sixth, right? What we do is we take this one, multiply by that one, and then multiply by that one, and then this one times that one, and that one times that one, right? Each term at a time gets multiplied. Then we need to combine them all together. So we get 21x to the seventh plus 14x to the ninth for the first one. And then the next one, we get plus 12x to the ninth plus 8x to the 11th, right? But this here is no good. We need to make sure we're simplifying that, right? So it should be 21x to the 7th plus 26x to the 9th plus 8x to the 11th. Right? Oh, I'm sorry, in descending order. We should go backwards. So 8x to the 11th plus 26x to the 9th plus 21x to the 7th. Make sure we're keeping them in descending order, right? Usually we do the largest first, right? Exponential descending order. Okay. Right, and integration and differentiation, right? Differentiate or integrate. Don't worry about the constants in integration, but take your power down by 1 and multiply, or divide by your coefficient, increase your power. Right? Do our right orders here, and always give back new results. Right? Any questions about the project? We got 1 week left on this one, by the way. And I'll fire up PyCharm while I pause for questions, because it's always slow for me. All right, no questions. That's cool. Easy. All right, come on, PyCharm, let's load. Okay, right, term node, it has the next term node reference, has its coefficient and its exponent. We're just going to assume integer exponents, but floating or doubles for coefficients. Right, but assume your exponents are always integers for now. I know that's not really the case, but we can assume that for now. We don't need to do anything too special. And then, right, taking the differentiation of anything x to the 0, right? Sure, just get rid of it. We don't have to handle too many special cases. Don't worry too much about all the different possibilities of what could go wrong. All right. Oh, PyCharm needs to update. All right, I'll have to update that. Where we looked at if we want to use an object in a dictionary, we need a hash so that we're not just comparing memory addresses. The default hash was not going to do what we needed. Yeah, unit plus unit tests. Right, so add and then unit test, make sure it works. So most of the time what you're going to do to make sure it works is just check the string output. It's probably your easiest bet there. So you can say, hey, if I take this and add another, here's what I expect to get with the string. And you want to make sure we're getting the good code coverage where, like, hey, if I get similar exponents, I need to combine coefficients. Make sure we're testing that. Make sure we're testing, hey, if I take a big one and a small one, I get the big one first and the small one second in my ordering, that sort of thing. If I were to subtract the negative, it's really like adding, that sort of basic checking there. So anything we're handling, we should be checking for in our tests. Yep. Cool. Yeah, good question, Sam. Thanks. Okay, so we need to make sure we can hash appropriately. And hashing needs to make sure that what we're hashing is immutable, right? We only want to hash immutable properties. Remember, and this is actually a really important concept, because if we hash off of something that changes, when we go try and find ourselves in the dictionary, we're not going to find ourselves. We're going to think we're a new object, and we're going to have an old object stuck out there in the dictionary. So if score is changeable for student, we don't want that to be included in the hash. It doesn't have to be, right? We could just leave it off here and say only name is hashed, because score could go up and down, right? So if the score property attribute of our class is changeable, don't hash it. That's fine. You don't have to hash every single attribute. What we want is a way to get a hash value for the object off of our immutable properties. Sure, if it's just off a name, that's fine. I mean, you want to try and hash something that will reduce your amount of collisions. Right? You want less collisions when you hash things. That's kind of the goal there. Okay? So less collisions when we hash. So we want to reduce collisions. So like hashing any of the built-in hashing strings, great. Right? Python knows how to do that. Don't reinvent the wheel. Other than that, you can do all sorts of fun things, and there's all sorts of theory around prime numbers and shifting and all the stuff that makes my head hurt. Right? Sure. But equals, now we want to check, hey, does my name and score equal? I'm the same object if my name and score are the same. Right? Or maybe we want to just assign a student ID number, and then we'll just check your student ID number, and then we'll assume you're equal if your IDs are the same. That sort of thing. Because if score changes, you're not equal to the other one. Maybe. You know, stuff can still crop up. So we have to be careful using hash tables and dictionaries with custom objects. Okay? And that's why we study them, right? We have to look at all these things and understand what all needs to match for that to work right, because dictionaries are phenomenal. We love using dictionaries. Okay? So we're not going to build our own right now. I think we'll probably save that exercise for the lab time, because it's essentially copying out of the book, which is not very exciting. And having to build your own is, you know, just copy pasting is silly. What we want to do is like try to understand, how do I build that oversized array for my data storage, and how do I find the hash and then mod it, get it in the right index, and then how do I do the chaining? Because we looked at, there's a couple different cases for how you handle collisions where two objects have the same hash but they aren't the same object. That's a collision. So we looked at, the book has all sorts of these. So this is our storage array, right? Again, some prime number usually, 1, 2, 3, 4, 5, 6, 7. We'll just say 7 for now, right? I get a hash mod by this, and I'll throw an object in here. If I already have an object here, right? If I already have an Eric here, well, I need to see, am I equal? Checking the equals method, because the hash was the same. If I'm not equals, I'll add another one here in a chain of objects with a singly linked list. Right? I just check each next, on and on and on and on until I either have not matched and I throw myself at the end, or I have matched and I just get to update it, right? Or give back, right? Depending on which way we're looking. Right? And this is all based on key, right? We do this all with a map, with a key and value. Right? So we have a key with an associated value. That's Eric, E-R-I-C. Oh yeah, that spells Eric. It's just kind of scribbly. Okay? So doing that process then, right? And then what happens when we resize our internal storage array, we have extra steps. Right? That n operation of copying, we don't actually copy anything. Right? When we need to make a bigger storage array, we go to the next, double plus to the next prime number, just throw out a bunch here. Say like 23 probably. I think 23 is prime. We need to take every object and rehash it. We don't copy it to the exact same index. I don't say, hey, all the Erics belong here at index 2, right? Because they were in index 2 before. No, I have to hash and I have to mod by the length to find the new spot where it goes, right? So the process there, for every item, I have to go rehash and remod to store in the new location in the new storage array. But still, it's n operations for for n items. I have to do some number of operations, and when we talk about performance, we get to throw away coefficients because we're fancy like that. Right? Because sure, 100 times n for every 100 operations for every n is still bad, but in terms of how that scales, it's still linear, still scales by n. It's not exponential, even if you're doing it 100 or 1,000 times, 1,000 operations per. Right? It still scales linearly. Linearly? Oh my goodness. English is hard. I'm gonna drink some more coffee. I gotta go get some more. I'm almost out. It's a bummer. Okay, so we'll work through that step there, I think, as our lab exercise, because that's worthwhile. Doing it by hand. Don't just copy it out of the book, right? Like, try and understand, hey, how do I size my array? Let me do the hash of an object. Let me mod it by the length and throw it in there. Other approaches, if they don't do this chaining approach here, you might say, oh, just put it in the next spot. But you might imagine the problem with that, right? Maybe this spot was full, and I had to go to the next spot, and the next spot was full, I have to go to the next spot, and the next spot was full, I have to go to the next spot, and I have to check a bunch of objects because they might have already had things there. So like as we start filling up a list here, right, I have to put in a bunch of like E, B, C, D, F, Q, I don't know. And we say, oh, here's an E, right? Okay, well, sure. I already have an E. Let's put it in the next spot. Fine. Let me add another one. All right, so here's E. I have to check this one, 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 check this one. Shows up here. Right? And you can imagine having to find the next one. There's a lot of overhead in trying to look in other hash locations that we shouldn't have to check, versus if you have a direct collision, then you just start the chaining. And people who are really good at math have solved this sort of problem, and they said, yeah, this is probably your best approach, right? Instead of just jumping to the next available spot. And then there's different fill ratios. Remember we talked about this as a fill ratio, right? So at what point do I want to resize? Because I don't want to get to 100% full. Is no good, right? We don't want to get to 100% full, because the more full you are, the higher likelihood you have of collisions, and collisions are slow, right? So what we want to do is we aim for some fill rate. I think it was around 70% or so, of saying I want about 30% free space, or at least 30% free space in my storage array to make sure I'm reducing the amount of collisions that I have. Okay, so instead of checking if we're full, we check if we've gone above our fill ratio. And we'll do those sorts of things in the lab for our exercise. Okay, we can look at different ratios and things like that. That's actually kind of interesting, is where you can check the fill ratio. So it's hard, random numbers, they're just the numeric value. So hashing them, sure, they just get their value. You get a relatively good distribution because our random generator is relatively random. Versus like when you hash strings, if we were to actually make a dictionary of names of all of the students at the college, right, we could do that, but you don't get a uniform distribution of names, right? Some names are much more common than other names, right? I mean, it's not the worst thing in the world, and maybe then you would hash first name and last name, and you're less likely to get collisions, and then we say that's fine. But if we're just hashing off of like first name, there's a lot of common first names, and we don't get that uniform distribution. So some of this, the math here for saying my performance, my average amortized, or my amortized performance here, relies on a uniform distribution. And we say, yeah, we'll probably get good hashes. Right? But we saw briefly, right, if I was stupid and I just said, hey, I'm just going to return 0 for my hash because I haven't figured out how to do this yet, it'll work, but it's going to put everything at 0, so I'm going to get a collision every single time I want to add something to a dictionary, which makes it really, really, really slow. Right? So we want to make sure we have good hashing to get a nice, good distribution of your values inside your hash table. That's what that's all about. Okay? So we want to aim for, or that's the goal, is a uniform distribution. That's the goal, right? We can't always guarantee it, but that's what we want to try. So if we were to use just random numbers, it would probably work out pretty well, but we could see, hey, like what kind of performance do we get checking different fill rates? And because we do chaining, right, what's fun here, because we have this chaining approach to collisions, you could actually fill to over 100%, right? If you say we had 1, 2, 3, 4, 5, 6, 7 values here. And let's just generate a bunch of random numbers, right? So just throw some numbers out at me in chat. Throw some numbers out, and we'll try and mod them by 7 and see where they're going to fit and see what's going to happen. Okay, just for fun. So throw a bunch of numbers out in chat. I'm going to see if we can throw them into our storage array. Okay, that mod 7, oh goodness. I'm going to pull up the calculator here. I was expecting smaller numbers. It's okay. It's good. So we want 88999 divided by 7. I want remainder. Where do I get my remainder math? Give me a remainder. Goodness. Okay, so 1.4, that's got to be 1/7. So the remainder is 1. So I'm going to throw that one here then at index 1. So that's 88999. Okay, I'm estimating here, right? I'm doing my best. So 389439 divided by 7. So, okay, same remainder. So I'm going to throw that in the same number. So we'll just chain that one here. That's 389439. 9 mod 7 is remainder 2. That one goes here. 6 mod 7 is remainder 6. That one goes here. 4 mod 7 is remainder 4. That one goes here. 45 mod 7, no remainder. It goes here. Okay, so I have 1, 2, 3, 4, 5, 6 values. 56. That's an even multiple of 7, right? So 56 goes here. So right now I have 7 values, but I still have open spots here, right? My chaining, 49, right? Multiples of 7 here, of course, go in here. 63, multiples of 7 go in here. My fill ratio right now, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 values out of 7 slots. I can do this. Nothing stops me from overfilling, having a larger fill ratio. Right? Again, the math around averages and trying to find this uniform distribution and when is a good time to make your copies or increase your size. Obviously, we don't want to increase our size less than some sort of geometric progression. We talked about, right, we need the doubling to happen, at least a doubling, so that on average when we amortize it, right, if you imagine those bar graphs, right, the amount of time it took, you could just lay it down, you could lay it down, you could lay it down, and we'd still get a nice a nice constant time operation, right, for our size. Right, it didn't grow, so the average time is still constant when we amortize. So you can play with different fill ratios and see, well, how long is it actually going to take me to do these operations? That might be fun to explore in the lab, like throw a bunch of values in, don't change the fill ratio, right? Change the fill ratio, throw a bunch of values in, see how long it takes, because every time we do double to accommodate those new values, it takes n operations. Again, we amortize it, but say if I'm going to throw 10,000 values in, do I really want to resize a bunch of times? And then there's additional cool things you can do. If you know your hash table is going to store 10,000 items, you initially size it big enough to store those 10,000 items so you don't have to do any doubling. Right, so there's a lot of really smart things we can do to optimize this. A lot of it's knowing the size of n is helpful, right, for anything. Right? With an array-based storage, we could just size it to size n when we started instead of having to do any doubling. And we get some really good adds. Okay, let's see. Yeah, I think we'll build out our hash table in lab on Monday. Again, it's mostly copying. We can do a slightly simplified version, but it won't be too bad to do that on Monday. And then we can maybe look at some runtime analysis. Again, runtime analysis isn't perfect because our computer multitasks all the time, but maybe we could look at doing some runtime checking for performance, right, with different fill ratios for fun. And again, there's no, like, this is the optimal best for every single case. A lot of it depends on how much you're adding, how much you're subtracting, right? If you're adding and taking items in and out a lot, or if you're just going to add a bunch of items and then keep it at that size, as here's like a lookup table, I'm just going to keep the entire time my application runs. Sure, right? We have different performance implications based on how this data structure is going to be used. That's the whole point of studying these, right? We'll look at what they're good at and what they're not good at and when we might want to use them. That sort of thing. Right, I think that's actually all we have today because we don't go super duper deep and we're going to do more in lab on Monday. So take the time, get working on your polynomial project if you're not done with it yet. Right, again, the polynomial keeps a reference of the first term node. So it's init, its constructor here, takes an int exponent and a coefficient to create the first term node. Right, so we shouldn't have empty polynomials. Right, we should always have a polynomial with a term. That's the idea there. If we check if we equal or not equal another polynomial, right, we have to check all the terms in a row, see if we have matching terms. If all of our terms are the same, we must be the same. Okay. Other thoughts, concerns, comments? And then next week, we're going to talk about our final project that'll take us through the end of the semester. I know one person had said they're not going to be able to make it to the final meeting. Again, I want to try and do like a synchronous presentation on Zoom where each individual or pair, right, can present their final project, and we can talk about it, show the results, and have a chance to discuss what we did. So we'll get to the final project next week. We'll be doing some analysis. It should be fun. I think it was really interesting last time we tried this. So that's coming up in the final exam slot. So in lieu of a final exam, right, we just have a final project. So 4/28, 6 p.m. is the idea for presentations. And there's not too many of us in the course, so it should work out well. That we'll all have time to talk about it. If you can't make it synchronously, that's okay. Let me know. We can look at some recording options or meeting with me, presenting it at a different time. Okay? That's actually all I have today. So next week, again, we'll move into search trees. We'll start talking about the final project, and we are at the tail end of the semester. You folks have done great. Apologies for not having stuff in graded. I started working on the projects, and life just keeps happening. So I'll be plugging away at those for you folks. So you can get your scores, and we can go from there. Okay? If you're not happy with your score, let me know. We'll see what we can do. I don't usually offer extra credit, but this final project is worth a lot, right, compared to the rest. So our final project being 30% of your overall score for the rest of the class. It's worth just as much as all the other projects combined. Okay? So hopefully that works out well in your favor. That we'll have lots of time to do this. We can work together, find someone in the course who you might want to pair up with, and we can go from there. All right, cool. I don't see any other questions in chat, so why don't we wrap it up? We'll call that a day. I've got office hours after class. If you guys want to meet, let me know. I'm happy to fire up a Zoom or call me on Discord, that sort of thing. And we can go from there. Should we go check out some math? Math is fun. We all like math. See if one of our favorite math profs is around. Yes, we've got boring math professor. He's my hero. He also plays the recorder, which I do not do. So we'll head over that way, shout out, say hi, and we'll go from there. All right, folks, keep in touch. Let me know how things are going. Again, it's a little funky not, being synchronous where I can get a lot of feedback, but yeah, let me know, and we'll go from there. If not, I'll see you Monday.